In this example, we're going to change things up. We're still going to use the shell method. We're going to find the exact volume generated when this region that's bounded between these three curves is rotated about the x-axis, which we haven't done yet with the shell method. So we have a horizontal axis of rotation, namely the x-axis, which is down here. Now, once you know that you have an x-axis rotation, you know that the rectangle must be parallel to that axis of rotation. It must be. All right, well then once you know that, then you know that the thickness is dy. You're locked in, which means I know that my volume function, if I write it, I know it has to be 2 pi integral from c to d r of y times f of y minus g of y dy. Knowing that I have the x-axis as my axis of rotation means I'm locked in for a parallel rectangle, which means I'm locked in for dy, which means everything has to be in terms of y. This is going to be trickier for us because we're just not as comfortable as working with functions of y as we are with functions of x. It's not as familiar to us because we didn't spend all of algebra and pre-calc doing it. All right, now let's figure out a few things. So we have these lovely curves here. So we have a curve, I don't know, I'll call it x1, which is right here, which is that curve right there. So that's x1. And then we have another curve, they call it a curve, but it's really a line, which I'll call x2, which is right here. It's this vertical line right here. Right? And then y equals 1, which is right down here. All right, so I want to find the region, or excuse me, I want to find the volume of the solid found by rotating that region around that x-axis. Okay, well, I already know the thickness part. Now, what about r of y? R of y is the radius, which we learn back in the, when this is first set up, that r of y has to be y. Right? We learned that back a few pages in the setup page, when we learned that if your rotation of axis of rotation, excuse me, is your x-axis, then r of y is y, because that's what this is. This is the distance from the axis, x-axis, up to that value. That's what y is, by definition. All right, so that part is y. So I know that my next step will be 2 pi. I'm going to have an integral there, but I know this piece is y. That part's done. And then I've got some other stuff in there that I got to figure out. And then I know it's dy. Okay, now let's figure out the f of y minus g of y, because that's the length part right here. This is the length of that rectangle, or the height of that rectangle, whichever way you want to think about it. Okay, so if I look here, I need to be able to find this length. Okay, well that would be, now remember, these are functions in y, so you're going back to the y-axis. So from here out to here is x1, and then from here to here is x2. So that length would be x1 minus x2. Right? So it'll be, if I want to think of it in terms of f of y and g of y, I'm turning x1 into f of y, which is this one right there. And I'm turning this one into g of y right there, because that's the outer and that's the inner for that region. Okay, so I will put that in. So f of y is 4 over y plus y cubed minus g of y, which was 1 over the square root of 3. That's easy. Last but not least, I need my limits of integration. Now remember, these are y values. So I want to look at the lowest y value, which is right here. There you go. That's the start. So that's easy, 1. So my lower limit of integration is definitely 1. But my upper limit of integration is going to happen right here. There's an intersection right here. And that's going to be the end. And I need to figure out what that y value is. Now I can go to Desmos and try to get myself a hint. Let me go to Desmos. I say only a hint because it doesn't work out nicely. So the y value is 1.7321. Okay, well, I know what that is just off the top of my head. Do you know what that is? Maybe? Let's see if I can kind of make a logic argument. All right, so let's think about this. If you want to find the intersection, you want to let 4 over y plus y cubed equal 1 over the square root of 3. There's not a good way to do this. This is proportion, by the way. So you can think of it as cross multiplication. What you're really doing is multiplying out both denominators. So you'll get 4 square root of 3 equals y plus y cubed. If you remember proportions from a long time ago, many classes before this. This does not have a good solution. This is what I was saying. There's no good solution for this. We don't learn how to do this in pre-calc. There are analytical methods, but they're kind of awful. So we kind of have to, at this point, realize, hey, that 1.732, isn't that the square root of 3? Yes, it is. So if we let y equal square root of 3, which is about 1.732, then you can watch what happens. What's y plus y cubed? Square root of 3 plus the square root of 3 cubed would be equal to the square root of 3 plus the square root of 27, because 3 cubed is 27, which is the square root of 3 plus 3 square root of 3, which is 4 square root of 3. It works. Right? 1.732 is the square root of 3. Right? So it's a decimal approximation, I should say, of the square root of 3. So there's no good analytic method for doing this. You're kind of using Desmos to kind of back yourself up, right? So thanks, Desmos. So Desmos gave us the hint of what this was going to be. And when you write out the equation, you kind of get the clue. So 1 square root of 3 plus 3 more square roots of 3, because that's what happens when you take the square root of 3 and cube it, will work out. It works. So this is actually the square root of 3. I'd love to tell you there's a better way to do that, and I'm sure there is, but that's the rough and dirty way to make that happen. And if you're looking for a decimal approximation, 1.732 will work fine. It's not the end of the world. But the square root of 3 is very important for how we have to do this by hand. You'll see what I mean in a minute. Okay, now I want to kind of make things a little bit easier myself, because I noticed that these two terms both have a y in them. So I can factor that y out and make it y times 1 plus y squared. Now, why am I doing that? Well, because I'm about to distribute the y to both of these terms. When I do that in that first term, they're going to cancel. The y and the y cancel. So that means that I have 2 pi integral from 1 to the square root of 3. And then I have 4 over 1 plus y squared minus 1 over the square root of 3 y. The y did not cancel on this back term, dy. All right, now if little alarm bells are going off in your head, they should be, right? Because that first term, we know what that integral is because we have our integration quick reference sheet. That's arctangent, right? That first one. So, and it's just got a 4 out in front, that's all. So you put 4 out in front and away you go. So this is 2 pi, and then it's 4, because there's a 4 there, arctangent of y minus, all right, now with this one, you'd add 1 to the power, so it'd be y squared, and then you reverse, or reciprocate that, so 1/2. So it's 1 over 2 square root of 3 y squared. And we're going to take that from 1 to the square root of 3. Like that. Sorry, I got a little of an angle going. All right, so this is 2 pi. And now we really got to work for it. Actually, I'm going to have to give myself some space here. This is the one part that really needs some steps if I'm going to show this by hand. So this is 4 arctangent of the square root of 3 minus 1 over 2 square root of 3. You know what? I'm just pondering my color choices here. So sorry, 4 arctangent. No, I'll just leave it. 4 arctangent minus 1 over 2 square root of 3 times the square root of 3 squared, which is 3. That'll be part. So it's that whole piece minus, and then we do it again. 4 arctangent of 1 minus 1 over 2 square root of 3 times 1 squared. Whew. Okay. Sorry, I know that's bugging you because it's bugging me. That's the square root of 3. Sorry about that. I forgot about my color choices halfway through. Okay, so there we go. So I'm putting square root of 3 in, and I'm putting 1 in, and I'm subtracting. Oh my goodness. Okay, so we got some work ahead of us here. This isn't too bad. It really isn't. So this is 2 pi times. Okay, now the arctangent of the square root of 3, you have to remember your unit circle. So let me draw you a quick unit circle kind of over here real quick. Tangent is sine over cosine. Tangent of theta is sine of theta over cosine of theta. So we need an angle that has a sine that's the square root of 3 over 2, but a cosine that's a half. That way it'll work. And that's pi over 3. Right? So this one's pi over 3. No problem. So this is 4 times pi over 3 minus, well, the square root of 3 squared is 3, so that's 3 over 2 square root of 3. That's all there is to that one. All right, then minus 4, there's another one, arctangent of 1. So I need, if the tangent, if the tangent of this angle is 1, that means that the angle had to have the same sine and cosine, which is pi over 4, because then the sine and the cosine are the same value, and it works out. So this is pi over 4. So minus 4 times pi over 4. Right? So this guy right here is pi over 4. This guy right here is pi over 3. Right? I'll say 4 pi over 4 minus, and then that's a 1 over 2 square root of 3. Oh, but it's minus a minus. Sorry, so that's plus 1 over 2 square root of 3. Okay, minus and plus, those are like terms, so those make 2 over 2 square root of 3. So easy peasy there. So it's 2 pi, 4 pi over 3. I'm done with colors. Minus 2 over 2 square root of 3, because 3 and 1 make 2. And that's actually going to cancel and make it just 1 over 2 square root of 3. And then minus pi, right? Because 4 over 4 makes pi. All right, combining this all together, we get 2 pi times pi over 3 minus, and if I want to rationalize that, that's the square root of 3 over 3. You know, you technically didn't have to, but you know, these canceled, and then I just multiplied both sides, or both the top and the bottom, by the square root of 3 over the square root of 3, right, to rationalize it, and turns it into that, which means I can factor the third out, and it's 2 pi over 3, and I have a pi minus the square root of 3 left over. And this would be feet cubed, believe it or not. Now I can check my answers with Desmos, because I have the integral calculations right here. So there's that integral of my original integral. I just typed it all in. You can type an integral with y, and there's 2 pi over 3 times pi minus the square root of 3, just like I said. So I indeed did all of my math correctly. Shockingly, it's true. Oh, what was the decimal of that? It was 2.952. So if we were looking for a decimal answer, we could say it's 2.952 feet cubed.